Good morning, everybody. So we will continue to discuss isoparametric elements as we were discussing yesterday. So let me bring up the slides. Can you now see the slides?
Yes, ma'am.
Yes, ma'am.
Okay. So this is where we stopped in the previous class. So we talked about four-noded quadrilateral elements. We have previously talked about three-noded elements. And we have seen how to obtain the stiffness matrix in terms of N1, N2, N3, N4 as functions of U and V, and to evaluate the integral, which is needed to be integrated for the stiffness matrix using the Gauss quadrature method. And then I told you that in this class, what I will do is I will tell you how to choose the elements, and once you have chosen the elements, how to decide on the element shape functions, which I need not give to you anymore. Because as you have understood by this time, that once you have the element and you have the shape functions, what you have to do next in order to obtain the stiffness matrix is quite the same for most cases. So now what we're going to do is we're going to try and set up some standard rules for generation of various families of multidimensional elements. So we're going to discuss various families. So let us see what I mean by various families. And multidimensional, of course, means that we are going to discuss 1D, 2D, and 3D. We've already discussed 1D and 2D, some elements, and you also realize that whatever we discuss in 2 dimensions can be very easily extended to 3 dimensions. Now, shape functions that we are going to discuss must satisfy the following criteria. C0 continuity between elements. What does this mean? I will discuss in the next slide. Function has to allow any arbitrary linear form to be taken so that the first derivative exists. This is what it means. That means you need to choose a function, and the function can have any linear form, any arbitrary form. Actually, it doesn't necessarily have to be even linear, any arbitrary form. What is important is that the first derivative needs to exist. The first derivative cannot be undefined. So what do we mean by the continuity of an element? An element is said to have C0 continuity if the variable phi, so that is the variable that you're looking for, that is the variable that you're going to solve for, and that, sorry. That function has to be continuous across interface between adjacent elements. You have already seen that when you take the one-dimensional case, if you have phi1 as the solution here and phi2 as the solution here, then phi1 and phi2 must give you the same value at the junction at the interface between these 2 elements. So phi has to be continuous. So phi1 and phi2 that you look for has to be continuous across the interface between adjacent elements. Here I have made another statement. I have said that Lagrangian elements have C0 continuity. You do not yet know what Lagrangian elements are, but I'll come to that. Now, this is C0 continuity. If your phi is continuous, as well as phi dashed is continuous, that means the variable, the function is continuous, as well as its first derivative is continuous across the interface between adjacent elements, you would call such an element, you would say that such an element has C1 continuity. However, so you understand the basic principle behind the concept of C0 continuity or C1 continuity. Having said that, we are not going to talk about C1 continuous elements. We are only going to talk about C0 continuous elements, because in electric and magnetic fields, we can work with C0 continuous elements, and that is enough for us. So what does it mean? That means phi has to be continuous. What is the gradient of phi, or what is the derivative of phi? E is equal to minus grad phi. So E. Electric field does not have to be continuous across boundaries. It is only phi which needs to be continuous. So the requirement of the continuity of the elements that you choose comes from the physics of the problem. Now, since we do not need continuity for the electric field, but we only need continuity for the potential, and we have the Laplace's equation in terms of the potential, therefore we are going to use C0 elements. Now, does it mean that we cannot use C1 elements? We can use C1 elements, but we do not need to. C0 elements are sufficient. So we will concentrate on C0 elements. Is this clear to everybody? So that is the one requirement that we have put. Next, let us talk about the discretization error. So you're using a numerical technique. You are not finding the exact solution phi, but you're finding an approximate solution phi hat, which will be found as a summation over a finite number of elements or finite number of points. We are choosing Ni in such a way that we can uniquely define a function, but that function need not be the exact function. And therefore, because of that, there would be a discretization error. Obviously, the discretization error will diminish. So you're basically kind of doing this. We've been discussing this many times. Piecewise functions you are choosing, whereas the real function may be something like this. So you would have some errors here. And this error just can be reduced if you choose a smaller number of elements. Now, this is the discretization error. And there will be a discretization error, however small, when you use computational techniques. But having said that, so basically what I'm saying is that because phi is not exactly equal to the phi hat trial solution, you have some error, and that is the discretization error, because you're not solving for the problem in continuous space, but you are solving for the problem in discretized space. You have an error. My next question is, can you think of a situation where phi and phi hat would be exactly the same? You will not have any discretization error if you find the solution, if you find phi hat subject to the boundary conditions properly.
Whenever we are considering infinite number of elements, in that case.
But we can't do that. In practice, we cannot do that. In practice, what can happen? What can be a situation such that phi and phi hat are equal?
Gauss quadrature.
That's only the integration. After finding using Gauss quadrature, you will solve by phi as k inverse f. Gauss quadrature finds k and f. So k, the integration will be okay. Exact. Maybe. Not always. In some positions. Even if they're equal, exactly equal, you're still not finding phi, you're finding phi hats. So in all our previous cases, we have chosen phi hat to be a linear solution. Now, it is entirely possible that your actual phi is a...
When our phi hat matches the order of the...
Exactly. Exactly. So you do not know what is the exact solution. It is possible that it's a quadratic function and you're trying to approximate it with a linear function. So in that case, you will have mismatches. But suppose you have it really is phi is actually a some linear function. In that case, if you find phi hat equal to ax plus b, subject to the boundary conditions, you will be able to find the exact solution. There will be no discretization error, theoretically. Okay. So sometimes it is indeed possible with a finite number of elements or even a single element, if the polynomial expansion used in the element fits exactly the correct solution. So what I mean is, this is the spline that we were trying to fit, if you remember, and we were breaking this up into small elements, and we were getting errors. Now we say that if we break if we increase the number of elements to an infinite number, we will be able to get the exact solution. But that is not possible. So what you are doing is, let's say you have just one element, you are fitting a linear solution. And you're finding it subject to the boundary conditions, phi 1 is equal to phi hat phi 1, phi at what? At 1, and phi at L is equal to phi 2. These conditions have been satisfied. So you have 2 points. So what you know is, you know that at this point you have this value, at this point you have this value. And using linear elements, you're going to fit a linear polynomial, to find a linear polynomial to satisfy the solution. So the only possible solution is, of course, this, because whatever your phi is must satisfy this here and satisfy this here. Now, between these 2 points, you can have only one unique solution. So the phi must also be this. So you're in this situation, phi will match your phi hat. Similarly for higher order polynomial, which means that if you do not have a linear function, if instead your exact solution is like this, it is possible to find the exact solution, the approximate solution can be made to be equal to the exact solution if instead of choosing a linear trial function, I choose a quadratic trial function. Is that right?
Yes, ma'am.
So if the polynomial function that I choose matches the exact solution, the order of the exact polynomial solution, then you will not have any errors. So basically, we would like to choose the polynomial of the correct order. The interpolation function phi hat should be chosen such that we can choose the polynomial of the correct order. But there is a problem because I do not know what order phi is a priori. So if I do not know, how can I choose? You understand what I'm saying? I am saying that in the finite element method, what we do is we break up the whole domain into small elements, and over each element, we choose a linear function. So far, that is what we have done. Now, if you choose a linear function, then you will have some error. Let us call it the discretization error. That discretization error can be removed if you increase the number of elements infinitely. So if you have infinite number of points, you have the continuous space. If you have infinite number of elements, you have the actual continuous domain. That is theoretically possible, but that is not actually possible. You cannot actually do that. But there is another way to circumvent this problem, and that is when you are choosing the interpolation or trial function, if you happen to choose a polynomial of the correct order, by correct order, I mean that it has the same order as the exact solution, In that case also, you will not have any discretization error. So for example, even if you take one element and you have two boundary conditions to be met, there can be only one single line, one function which satisfies those conditions. Similarly, if you have a quadratic function and if you have three boundary conditions, 3 points, there can be only one function which satisfies those boundary conditions, and therefore you will be able to find the unique exact solution. So therefore, we should try to choose our interpolation function accordingly. We should choose the interpolation function such that it is a polynomial of the correct order. And when I say correct order, I mean that the order should match the polynomial, which is the exact solution. The problem here is that I do not know a priori what is the order of the exact solution. So what should I do? That's one aspect. The other aspect is, if let's say I have figured out by whatever means possible that I do not want to choose a linear polynomial function as my trial function, I need to choose a second order function. How will I do that? A second order polynomial should look like this. Instead of looking like ax plus by plus c, it will look like ax squared plus by squared plus cxy plus dx plus ey plus f. Of course, a, b, c, d, e, f coefficients can have many values, and some of them can even be 0. Now, what we actually do is we choose summation ni phi i. Phi I are constants. So if I want to choose a particular order of the polynomial, if I want to use a second order polynomial, I must choose the shape function accordingly. So my shape function should be a second order polynomial. If phi has to be a second order polynomial. So far, what we have done is we have considered, if you look at the we have considered one linear polynomial, linear in U, linear in V. So what this is going to give me is N1 phi 1. So when I put this phi into N1 phi 1, my phi hat will be a linear polynomial in U and V. If I want to find phi as a second order polynomial in U and V, the only option open to me is to choose N as second order polynomials in U and V. So do you understand the point I'm making? The point that I'm making is this, that if I want to choose a second order interpolation function, I have to choose my shape functions accordingly. So the shape functions determine sorry. Can you read it? This is clear to everybody?
Ma'am, how I can define the order of the trial function?
That I'll come to later.
Okay.
But this is what I need to do, is what I want you to understand at this point of time. Teja? Girish?
Yes, ma'am. Yes, ma'am.
What did you understand?
For the trial function to be with for having a errorless exact one, choose a trial function which is of same order. For that, order of the shape function should be the same of a trial function.
Okay, good. Apart from that, I want to just define what is called the rate of convergence. Now, look at this. Phi is being approximated as phi hat. And if I can expand phi at phi I. So let's say at the ith node, the value is phi I. I do not know the actual phi I, but phi hat gives me, if I expand it, it will be of this form: phi I plus del phi del x at I into x plus del square phi del x square at I into x square, and similarly for y. This is your Taylor series expansion. Now, suppose you decide that you are going to use a first order polynomial, which means you're going to use a linear polynomial. Which means, what are you going to do? This goes on for infinite number of terms, and we cannot consider the infinite number of terms. So if I choose a linear function, I'm basically curtailing here. X squared and all higher orders are ignored, and y squared and all higher orders are ignored. So I will come up with a solution like this. I'll write it here. This is my linear polynomial, which I may be writing as Am I making myself clear?
Yes.
So essentially what I'm doing is I am ignoring all terms above x squared and higher. In this case, I will have an error. I cannot evaluate the error, but what I can see is if within an element of size h, a polynomial expansion of order p is employed, then it can fit locally the Taylor series expansion up to that order. So I will, this will be fitted, this value, and this value I will be able to find exactly, but these values will not be there if I choose a linear term. In which case the error is of the order of hp plus 1. So if p is equal to 1, then the order is of the order h squared. What does it mean? It would mean that in that case, I would expect a convergence rate of the order of h squared. That is, if you reduce h to h by 2, your error will automatically reduce by h by 4, that is 2 squared. Okay. So we cannot evaluate the error, but we can evaluate the rate of convergence, which means that we do know that if we take smaller elements, we will have less error, and the solution will converge to the exact value faster. So if you choose a linear polynomial, then the moment you halve the element size, your error will be reduced by 4 times. So that is what I know. Similarly, if I take a second order polynomial, so I will be including all these terms and I will be ignoring the terms above this. So when I find the solution, I will be matching exactly the Taylor series expansion up to this. Okay. These terms will be exactly matched, but terms above this, which will have x cube and y cube, will not be matched. So in that case, I will say the error is of the order of 3. And if I reduced h by half, I will reduce the convergence error by 1/8 times. Are you getting my point?
No.
All this
So basically, if we know the order, we may not be able to evaluate the error, but we will be able to predict the exact solution as a monotonic function. So we will have some estimate. So what are the errors that you have? You have discretization error, which I have just discussed, because you are approximating a function with a lower function. And you have roundoff errors in computers. Well, this was a concern when finite element first came into the picture when we were working in the 70s or 80s. But nowadays, the kind of computers you use, you really don't have to bother about the roundoff errors. So as order of the element increases, the convergence to the exact solution becomes rapid. So when you take, instead of a linear polynomial, you take a quadratic polynomial, it is possible that you will get the exact solution even if your polynomial is not linear, but quadratic. If it is cubic or above the exact solution, you will not get the exact solution even with the quadratic polynomial, but the convergence to the exact solution will be faster. Which means that it makes sense to take a polynomial of higher order than a linear polynomial. And when I take a higher order polynomial, basically what I'm doing is I'm increasing the shape function of my element. So I would say that the order of the element is increasing. So as the order of the element increases, the convergence to the exact solution becomes more rapid. We do not know the magnitude of the error, but it is clear that we should seek element shape functions with the highest complete polynomial for a given number of degrees of freedom. So we should try and choose a higher order polynomial, but we do not always do that. So that is what the next discussion is going to be about. Any questions so far?
Whenever the third order part is not matching, then in that case the error will reduce by 1 by 4. So
1 by 8.
1 by 8.
Yeah.
Okay, then if we match the fourth part, then it will be 1 by 6.
Yeah.
Okay.
No, I didn't get the 1 by 8 part.
I have not proven it to you, I have just given it to you. If within an element of size h, a polynomial expansion of order p is employed, then it can fit locally the Taylor series expansion up to that order. Error of the order is hp plus 1. So if your p is equal to 1, then error is of the order of h squared. So you are ignoring terms which are h squared and above, because you're having del square phi del x squared. In that case, one would then expect a convergence rate of the order of h to the power p plus 1, so p squared. That is, the error will be reduced to 1/4 for having a mesh spacing, for halving the mesh spacing if p equal to 1. Okay.
Yes, ma'am.
Ma'am, I have one doubt.
Mm.
So in the Taylor series expansion,
Mm.
actually bifactorial should be there, no, ma'am, like dou by dou x.
Yeah, I'm not concerned with the constants here. I'm just looking at the variable. So here you have x square, y square, and you have some values, some coefficients. And when you choose a second, you will choose a plus bx plus cx square, and so on and so forth. So you will have these terms, and these terms you will try to, these coefficients will try to obtain by whatever means we have discussed. So you will try to fit the coefficients. But the terms that you have not considered, you cannot fit. So you're actually ignoring those terms. So that is the point I'm making, that you can find the coefficients of x square, y square if you take a second order element, but you will still be ignoring terms which contain x cube, y cube, etc. And therefore your order of convergence will be accordingly.
Okay, ma'am. Thank you.
Okay, now, after all this discussion, I'm going to give you an element of my choice. What you see is let's say this is X, this is Y. In the X direction, you have these two, only the edges. This is one element. And along the Y direction, you have mid-side nodes. So you have nodes also in the, not at the vertices, but at the mid-sides, or the sides, along the sides, in the middle of the sides. Now, I have given you this element, and I want to find the shape function for this element. I've just now told you that we can choose an element, and accordingly, we have to choose the shape functions. And how we choose the shape functions decides the interpolation function that you use for phi. Now, what kind of phi would you be able to fit to this element? So depending upon the interpolation function, phi or phi hat will have a certain shape over this element. And of course, you have phi 1, phi 2 given here, known or unknown. So my question is, what kind of an interpolation function would you be fitting to this element? Do not read, you will not understand. Just try to think. So I have to find an unknown function phi, which passes through all these nodes. These values at these nodes have to be satisfied. So I need a polynomial. It cannot be a linear polynomial. What kind of a polynomial will be uniquely defined by 8 points? How many terms would you have in that polynomial?
8 terms.
8 terms. So what kind of terms would these be? Can you give me the terms? One would be like a constant. Then bx.
Bx square plus dy plus ey square plus fxy.
I've got 6.
Cubic term will also be present.
Which cubic?
X cube and Y cube.
Now we have to ensure inter-element continuity, which means that along the edges, the function must be uniquely defined. Now, if I have to define a function uniquely, it must be something like this. So 4 points means it must be a cubic spline along Y, cubic spline along Y. But along the X direction, you have only 2 points. So to uniquely define a function along by 2 points, what kind of function can you uniquely define by 2 points? I can think of something like this, but would it be unique?
Linear.
You can only define a linear function uniquely. That means your solution has to be linear in X. You don't have enough information. So because you have to ensure inter-element continuity, therefore phi has to be uniquely defined along this edge. Phi has to be uniquely defined along this edge Phi has to be uniquely defined along this edge, along this edge, along this edge. So on all the 4 boundaries, phi has to be uniquely defined. When I have 4 points, I can uniquely define a cubic spline. But when I have only 2 points, I can uniquely define only a linear function, which means I'm looking for a function phi. I'm looking for a function phi, which is linear in X and cubic in Y. Because that is the kind of function I can uniquely define over this element. I cannot do any better. Is this clear to everybody?
Ma'am.
Yeah. Okay. And we must also remember that we have to ensure C0 continuity, which means we have to ensure the existence of the first derivative. So all the linear terms, a plus bx plus cy, must be there. See, the point is, you have 8 points. So you can have only 8 coefficients. Now, if you're thinking of a cubic term, if you're thinking of a cubic polynomial, how many terms does a cubic polynomial have? A cubic polynomial in X and Y. How many terms will it have? There are only many terms, right? And there is a way of figuring out what those terms are. This is your Pascal triangle. What does the Pascal triangle do? The Pascal triangle tells me what are the terms that must be there. So the first order, you have these 3 terms, right? This is a complete, so this is a complete polynomial. What does it mean? But what do I mean by a complete polynomial? All the terms that are possible are included. Now, it might happen that a is equal to 0 or b is equal to 0, where you may get a plus cy, which is again a linear polynomial, but b has a value 0. So you actually should ideally include all these terms. 3 terms. A complete polynomial of order 1 will have 3 terms. A complete polynomial of order 2 will have 6 terms, 1, 2, 3, 4, 5, 6. A complete polynomial of cubic order 3 will have 10 terms. So a plus bx, okay, I'll not use ab, a0, okay? This is a complete polynomial of order 3. So that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 terms. So to uniquely define a polynomial with 10 terms, I need 10 points. But in the element that I have given you, there are only 8 points. So you cannot choose this function. You will not be able to identify this function. So you will have to drop some of the terms. When you use that element to find phi hat, you will have to drop some of the terms. Which are the terms that you will drop? You cannot drop the linear terms because, as I say, C1 continuity has to be there. So this has to be there, this has to be there, this has to be there.
Excuse
Now,
me. X
Yes,
cube. A6 x cube should not be there.
A6 x cube should not be there. Why?
My next direction only 2 points.
In X direction, you only have 2 points. So therefore, this cannot be there. This cannot
X.
be there. Right?
Yes, ma'am.
You cannot have the higher order term. So how many are you left with? 1, 2, 3, 4, 5, 6, 7. Should have 8. So which can I retain? So I will retain all the terms which have only the first order x. So I have a1, a2x plus a3y, these 3 linear terms. Then I have a4xy, a5y square, x square is dropped, but xy square is retained. Y cube, x cube is dropped, y cube is retained, and a8 xy cube is retained. So all terms which have x first order are retained, and all terms of y are retained. And I get 1, 2, 3, 4, 5, 6, 7, 8 terms. I think I had missed this term in the previous slide. So is this clear? What are the terms that we have to consider? So now I have 8 points and I should be able to obtain these 8 coefficients. If I am able to obtain these 8 coefficients, I will be able to find the approximate the interpolation polynomial phi hat. This is of course phi hat. I will also be able to find the shape functions. Remember, that is what I set out to do. I want to find the shape functions. So if I have this interpolation function, so basically this is now, if you remember earlier, what we were doing is we were starting with some trial function ax plus by plus c, and then we were going on to show you that whatever shape functions I had given you is equivalent to choosing a linear trial function. Now I am choosing a trial function with 8 terms. And I want to find the shape functions without being given the shape function. Now this means that at the 8 points, phi I must be satisfied. So I can write this phi I is equal to, so phi 1, phi 2, phi 3, etc. 1, x1, so this is point number 1, x1, y1. I will write the equation for x2, y2, x3, y3. So I will have 8 equations for phi 1 to phi 8. And I need to just solve these 8 equations to be able to find the 8 coefficients, right? I have 8 simultaneous equations. And solving them, I can get the 8 coefficients, right? So let me call this the coefficient matrix. This is your coordinate matrix. This is your coefficient matrix AI, which has A1, A2 up to A8. Phi I is the nodal vector. So phi I is equal to C into AI. So taking AI to the left-hand side, AI can be written as C inverse phi I. Now, this comes from this above equation. Now, if you look at this, phi is written as P into AI, where P is 1, x, y, xy, y square, y cube. These are the variables, not the coordinates, right? So I can write phi as P into AI, and AI I have obtained as C inverse phi I. So once I write this, my phi is equal to P C inverse phi I, which is like N phi I, which means PC inverse must be equal to N. So therefore, N, I have obtained the shape function N as P into C inverse. N is N1, N2, N3 up to N8. There are 8 shape functions. And if I know P, I can find, so I need to find P, N as a function of X and Y. Once I find it as a function of X and Y, I mean, this X and Y is basically U and V. If these are your natural coordinates, you can find them in U and V. We are not finding them in, so these are isoparametric elements, or if you work in the physical domain, they are the actual shape functions, does not matter what. Whatever you do, you can find n as n1 up to n8 as PC inverse. C inverse is given by the coordinates and P is given by the interpolation function. So which means that if I give you an arbitrary element, let's say I give you an element like this, you are now in a position to find the shape functions for this. Is this clear to everybody? So
Yes,
once you have an element, I have not told you how to choose an element. I have discussed some aspects of the elements that we are going to choose. Over and above that, I have given you a technique to find a shape function, provided the element is given to you. So you will have to look at the elements and you will have to see what is the variation in the U domain or X domain and the variation in the V domain or Y domain. What kind of variation can be uniquely defined? Accordingly, you will choose a polynomial which may or may not have the complete polynomial in that order. If it is possible, you will retain the entire complete polynomial. If it is not possible, you will not retain the complete polynomial. You will retain the correct order of terms. So for example, to give you an example, if I'm going to do this, as you can see in this case, you can uniquely define a quadratic equation in this direction, also in this direction. So you can have a quadratic equation, quadratic function in X as well as Y. Now, if you have to do that, if you look at the Pascal's triangle, for a complete polynomial of the second order, you need 6 terms. 1, 2, 3, 4, 5, 6, 7, 8. You have more than 6 terms. So what will you do? You can maybe have
XY square.
right? You can probably do this. So yeah, so now once you do that, you can find the shape function. I will stop here, and this is, I think, our last class before your midterm. So this is what will be there for your syllabus. When is the exam?
Thursday.
It will be a pen and
morning.
okay, it will be a pen and paper. So there might be some questions which you can answer on the computer directly on Hello, and there might be some questions which you may have to write down with pen and paper and upload by scanning. I hope you have all submitted your assignment. You will need to know how to do the MATLAB programming. Okay, if there are no questions, I'll stop here. Balaji, remind me to give them the slides up to this.
Yes, sir.
Okay, then we'll stop here. And you cannot upload anywhere else. You will have to upload on Hello. If you have any difficulty, you will have to inform me immediately, me or Balaji, immediately before the time is up.